Hey guys, welcome back to Core Academy. In this series of video, we are looking into Nvidia Cuda programming. In this video, we are going to look into Nvidia Cuda architecture and the device programming model. So in the Nvidia Cuda programming, I just want to start with the comparison of CPU versus GPU. CPU stands for Central Processing Unit and GPU stands for Graphics Processing Unit. So on the left side of the block diagram, you can see CPU architecture where you have multiple cores. For example, some CPUs will have like dual core, octa core, and things like that. Okay, and you also have the cache memories at various hierarchies: L1 cache, L2 cache, L3 cache, and eventually you also have DRAM. So DRAM is basically dynamic random access memory, where the latency of accessing data from DRAM is significantly higher than accessing data from L1 to L1, L2, or L3. On the right side, you see the graphics processing unit architecture where you have multiple cores. So see, if you compare the left side and the right side, left side has like limited number of cores, whereas on the right side you have several cores available which enable us to do parallel computing on GPU. Similarly, you have cache and DRAM, which is same as the CPU. You have dedicated DRAM for CPU and dedicated DRAM for GPU, which means that if you have to do some processing on the GPU, you will have to copy the memory contents from the CPU memory to the GPU memory. The GPU memory is also called as device memory, whereas the CPU memory is also called the host memory. So before we go to the next slide, I think I want to highlight certain things on the CPU versus GPU architecture. So let's turn on the pen. So this host is sometimes also called, CPU is also called as host. Okay, host, and GPU is also called as device. Yeah. So before we go to the next slide, I think I want to highlight one more thing. Anything that you want to execute sequentially will have to be done in the CPU. Anything that you want to execute concurrently or parallelly, you can do it in GPU. One simple example is like there are certain operations where you will do same on a large amount of data. For example, if you take an image, you will have to do the same operation on each and every pixel. Just think about taking a point operation in an image processing, so where you take a pixel and combine with yet another image, or changing the intensity of the image. So the pixel wise operation is pretty much same across the entire image. So this operation can be done in parallel. We don't have much dependencies on the previous data, things like that in certain operations. So one other example is basically matrix multiplication. Matrix multiplication relies on computing the same operation for each and every element in the matrix. So such operations can be done in parallel, whereas things like where you have to do sequentially, let's say you have a lot of comparisons, if else comparisons, such kind of things has to be done sequentially. That has to be executed on the CPU, and anything that you can run in parallel can be run on a GPU. An example is basically any graphic application or image processing application can be executed on the GPU, whereas the generic programming can be done on the CPU. Okay, let's move ahead. So this is basically a basic CUDA device memory model where you have the host here. The GPU program is basically loaded by the host. So this host will be loading the GPU program, which we call it as a kernel. And on the device side, you have multiple blocks. So each host will basically get an access to a grid. This is the high level memory model or high level device model. And each grid has multiple blocks. This number of blocks is actually dependent on the GPU architecture you use. typically it will be like each grid will have like 512 blocks or 1024 blocks. We'll get to know and see how we basically check how many number of blocks available per grid using the CUDA programming. Okay, and each block will also have some shared memory. Okay, so I'll provide more details about this shortly, but basically what happens is each block will have some shared memory. So you can see shared memory for each block, and there are multiple threads available in each blocks. So this shared memory is basically used by all the threads in the block. Okay, so let's say if the block has like n threads, all the n threads can access the shared memory, but the shared memory cannot be accessed by the threads in the other blocks. Okay, for example, this thread cannot access the shared memory of block 00. Okay, so thread 00 of block 00 can only access the shared memory of block 00. And on top of it, you also have something called the global memory. You also have constant memory. So global memory is the memory that we allocate using CUDA malloc or something like that. So the host is basically responsible for transferring the data from the CPU memory to the device memory. So any memory that we allocate is basically part of the global memory. And there is also constant memory. This is a read-only access memory accessed by the kernels. This is kind of a fast access memory because we don't write, so there won't be much of retention, or there won't be the coherency issues. We will only be reading the contents, so it's typically faster than accessing the global memory. And shared memory is basically sitting closer to the thread. They are basically accessed only by the threads. On top of it, we also have something called registers. These registers are available per thread, and they can only be accessed by the threads. So these are basically uh, anything we declare a local variable, they all will be allocated in the registers. Okay, so registers are the fastest memory that we can access. Now let's go on deep for so each kernel, as I said earlier, get access to a grid, and each grid has multiple blocks. So we'll see how many blocks we get per grid using the CUDA programming. But assume that this is something we have control. So we can define how many blocks we want per grid. We can also define how many threads we want per grid. How many threads we want per block. So in this example, you can see this grid has a 2 by 3. So you have 2 rows and 3 columns. So 2 by 3 blocks, and each block has 2 by 4 and 2 by 4 by 2. So basically what happens is that the block is basically consists of three-dimensional threads. So that is why you see 0, 0, 0, 1, 0, 0, 2, 0, 0 here. So you see here, this is a three-dimensional. So each block has three-dimensional threads, whereas each grid has only two-dimensional blocks. Okay, so you only see two numbers here. So a grid contains two-dimensional blocks, whereas a block contains three-dimensional threads, which we'll see shortly. Okay, so that's all about the CUDA grid blocks and threads, and this is something we have complete control of how many threads we want to allocate per block and how many blocks we want to allocate per grid. Of course, there is a maximum limit, but we can define within that maximum limit. Okay, now let's dive into the programming model. So here, let's go and CUDA. So I'm going to first show you how many GPUs we have. So when you run Nvidia SMI, you will see the number of GPUs available here. So here you can find four Nvidia GPUs available, Nvidia RTX 6000. Okay, so we have four GPUs available in the system. Now let's go and access these GPUs. Let's first define. So for any CUDA programming, we'll have to either use stdio.h or iostream depending on what kind of programming you want to write. I'm going to mix C++ along with the CUDA API, so I'm using iostream. And for any CUDA programming, you will have to use CUDA runtime.h. And here I'm writing a main program. Okay, so I'm just returning 0 in case of success. Now let's first get the number of GPUs available in this system. We of course got 4 GPUs using the Nvidia SMI count, Nvidia SMI command. Now let's see if we get the same device count using the CUDA APIs. So CUDA get device count will basically return or provide us the number of GPUs available in the system. So if it is not success, I'm saying there is some problem with this API. Okay, so failed to get the GPU device count. Okay, now in this case I'm basically returning -1 because I didn't find the number of GPUs. Okay, so in case if it succeeds, I'm printing the number of GPUs, which is basically count. Okay, so now let's go and compile. So the way to compile is you should compile this program using Nvidia C compiler, which is nvcc, and I'm giving program 01.cu, which will generate .a.out file when I run that. So I got the number of GPUs 4, which is basically the same that we saw with the Nvidia SMI command. So we have 4 GPUs, 0, 1, and 1, 2, and 3. Okay, now let's add more details to this program. So I want to get the properties of the GPU using CUDA programming. So I know the number of GPUs available now. So let's get the properties of each of the GPUs. In our case, all the GPUs have the same property, so it should be getting the same properties pretty much for all the GPUs. So in order to get the properties of the GPU, we use a API called CUDA get device properties, and you will have to pass this CUDA device prop variable. So as usual, I'm just checking if the API has succeeded or not. Okay, so in this case, if it's not succeeded, I'm just printing an error saying that failed to get the GPU device properties. And in this case, basically I'm returning -1 because it's an error case. And if I get it, okay, so I'm basically in this case, let's first print what GPU is this. Basically GPU 0, 1, 2, 3 in case of 4 GPUs. In order to differentiate, I'm just printing some magic string here. Okay, and now let's print the GPU name, which is basically you get prop.name. We got prop for each of the yeah, I think I made a mistake here. Let's fix it. So for the CUDA get device properties, we'll also have to pass the device number, okay, which is basically I in this case. Now let's go and compile this program again. Okay, let's run. So when we run it, you see there are 4 GPUs. GPU 0 is Nvidia RTX 6000 ADA generation. All GPUs are pretty much same. Now let's go and print more details of the GPU. So we got name from the prop. Now let's print more. Oops. Okay, so let's now print the available memory for each of the GPU, which is basically prop.total global memory. This is nothing but the global memory I was showing in the block diagram. Okay, and then you also have shared memory per block. I was showing shared memory per block, so which can be accessed by shared mem per block. Okay, and then you also have registers per block, and these registers are basically divided between the threads. But let's print how many registers we have per block here. Okay, and you also can print max threads per block. So max threads per block, which is basically max threads per block. And there is one other interesting thing called symmetric multiprocessor. I will go over what is that multiprocessor in a later video, but just for the sake of completeness, let me print that as well. Multiprocessor count. Okay, now let's go and compile this program. nvcc program01.cu, and after successful compilation, I'm printing this. You can see the GPU name, and then total memory is something like 50 gigabytes, I guess. So here basically this is kilobytes, and megabytes, gigabytes. So you have 50 gigabytes per GPU, and then the shared memory per block is like 49k, and then you have like 64 KB of registers per block, and you have like maximum threads per block. I was saying that each block will have something like 512 or 1024 threads. So in this architecture we have 1024 threads per block, and we also have something called multiprocessor 142 symmetric multiprocessor. I will go over the detail of this multiprocessor in a later video, but for now I think the most important things are the global memory, shared memory, registers, and max threads. Okay, so these are the important steps. On top of it, I was explaining you about blocks, threads, and how to access this, how to allocate these blocks, how to allocate these threads. We will go over that concept in the next video because it's somewhat interesting one, and also we'll have to go a little deeper to understand what that block means, how to allocate, with several different examples. So if you like this video, subscribe to this channel, like this video, share it with your friends. Until I record the next video, I'm signing off. Subscribe to the channel and follow this channel for more interesting AI related contents. Thank you, friends. Bye.